This is the different types of materials, different types of things you may see every day that you work with. And as you're thinking about those adhesion challenges, by no means is this an extensive list. I listed a couple things here. You may have come up with these already in your head. Maybe this is brand new to you, or maybe you're just on this webinar today to learn a little bit more about the options available to you. I'm not going to go through all the common automotive applications, but these are different applications that we've seen and that we've been able to address those adhesion challenges. Things such as paint adhesion on plastic components. As we change our plastics, a lot of times there's different things mixed in with the different injection molding. Therefore, your ink, your coating, and your paint doesn't want to adhere to it. We've been able to help a lot of customers with this, painting different types of bumper parts and dashboards specifically. That comes up a lot. Rubber seal adhesion, that's another thing as well. Being able to apply different types of seals and gaskets to metal components, trying to get better bondability between two materials that just really don't like to adhere. Whether it's they're not adhering at all or we're just trying to get a better pull strength between the two, that's something we've been able to address and solve for quite a few customers out there. Another big one, just to kind of point out one other, is the headlamp lens adhesion. Being able to make sure that that silicone adhesive that you've applied to the lens stays bonded. You're not getting any moisture inside of the lens itself, and that headlamp has more longevity to it. We've all seen the moisture inside the headlamps on the old car driving around town. Perhaps you might have that. Have one yourself that has that problem. So that's actually something that's become more of a norm, and I'll talk about that a little later more in the presentation. So in a nutshell, materials we work with, pretty much everything out there. Plastics is a huge thing. We work with fluoropolymers, something with very low surface energy, which Ryan will be chatting about in a minute here. Silicones, glass, metals, you name it. Pretty much, we've even worked with organic materials. So pretty much any material out there is a candidate for surface treatment. There's a couple dynamics that come into play when we work with materials. Adhesion depends on many factors. It can depend on the material type. It can depend on the different types of the additive loads, what's mixed in with the plastics or the metals, the chemistry, the roughness, so the physical bonding sites on the top of a plastic or a metal or a silicone, and then, of course, the chemistry itself. So we take all of these factors into play and then come up basically with what we call a surface wettability. And I'll have Mark go to the next slide here and chat a little bit about that. So imagine the surface of that material that you're thinking about right now, you're having a hard time bonding to. You're going to put a liquid on it. That liquid could be an ink, it could be a coating, it could be an adhesive. When that liquid molecules are stronger than the forces of adhesion, the liquid stays beaded on the surface. We call this cohesion. Our goal is to create more adhesion to the surface. A really good example of this is if you can think of a well-waxed car. A well-waxed car, the water molecules on that car stay beaded up. They don't want to wet out. They don't want to grab onto the surface. That is what we call low surface energy. It doesn't have good wettability on the surface. Now think of that same example. Think of a very old unwaxed car, and that water molecules sit on the surface of that and wets out really nice. That would be a good example of wettability, and that's ultimately what we're trying to do here with your ink or your adhesive or coating. So things that will impede good adhesion are low surface tension. I use the word surface energy as well. It's another way to refer to surface tension. We also refer to that in dynes, and Ryan's going to talk a little about dyne testing here in a bit. Migration of formulation components, mold release, temperature, UV light. There's mechanical stresses. This is huge in the automotive industry too. The more mechanical stress you have on the actual part itself can be an adhesion impediment. And then, of course, design and fabrication. You might come up with a great design. Sometimes marketing comes up with that fabulous new product and didn't really think about how we're going to address the bondability of the two products together. So in a nutshell, then we start asking what's a new material. I like this graphic here because it kind of takes all of that information I just shared and put it into one visual example. We have low surface energy, low dyne readings. The plastic surface, but you could also be looking at a metal or a different type of material as well. We've got contamination. We have oils, we have residues, mold release, something on the surface. Something's migrating to the surface that's causing that ink to not adhere correctly. And ultimately, we have limited bonding sites. Physically, there isn't a lot of area for that ink or coating to grab onto, creating that hydrophobic surface, that surface where that water is beating up and or that ink, that coating is beating up and wiping off the surface. I'm going to turn the mic over now to Ryan. Ryan's going to talk a little bit more in detail about what plasma does to help address those specific challenges.
Thank you, Sarah. One of the questions we get all the time is, what is plasma? And a very simple answer is a plasma is an ionized gas. But let's talk a little bit more about how it improves adhesion. So plasma treating improves adhesion in 3 ways. It's going to clean, etch, and functionalize the surface. And we'll dive into these more right away here. So let's first talk about how plasma treating cleans the surface. So plasma treatment removes both organic and inorganic materials from the surface. This helps create a cleaner surface. Sarah's going to dive into applications further, but one of the areas that we use cleaning quite a bit is cleaning with metals. It might be cleaning a cutting fluid off of it. It might be oil residue left on a material. But plasma treating is a great tool to clean the surface, particularly in metals. Additionally to cleaning, plasma treating also etches the surface. And sometimes when we say etch the surface, we'll have customers ask, ooh, is this going to change the appearance of the material? And what we're really doing is we're micro-etching the surface, something that you should not see with the naked eye. And what this does, it increases the surface area, ultimately creating more bonding sites. This slide illustrates that very well. The image on the left is a polyethylene film prior to plasma treatment, and that same film after plasma treatment. You can see with significant magnification here that the surface is much rougher in the picture on the right, that is after it's plasma treated, and that creates just more bonding sites for your ink, your adhesive, your coating, whatever it might be you're trying to adhere to stick to. In addition to cleaning and etching, plasma treatment also increases the polar groups on the surface of your material. This again affects your surface adhesion properties of the material that you're working with. Our goal in treatment is to transform a surface from a hydrophobic to a hydrophilic surface. Sarah talked about that a little bit in the slide earlier. The images here illustrate the change that a surface goes through when we're talking about cleaning, etching, and functionalizing a surface. You see the untreated polypropylene looks very different than the plasma-treated polypropylene on the bottom image of this screen. So that is just another microscopic image of what you'll see on the surface if you're looking at it at that level. So Sarah talked about probably one of my favorite things to talk about and to relate this to, and that's the freshly waxed car. And the picture of the dog that we're seeing here on the left is a great illustration in printing what happens. The top half of the image has been plasma treated while the bottom half is not. So you'll see that that top part of the image, the ink is wetting out. The bottom half, it is not wetting out. You see the droplet function that's sitting there. And that's exactly what you see, even though this is printing. If you're looking at maybe an adhesive application, the same thing is going to happen in those applications as well. So we really want to make sure that we're dealing with both the force of cohesion, understanding the impact of that with your material, as well as then how we can transform that to take advantage of the forces of adhesion. Sarah talked about this slide a couple of minutes ago, but let's review it for a minute. Inherently, any plastic surface is going to have a low surface energy. There's going to be 3 things that affect that surface energy and good adhesion. Contamination on the surface. This might be dust, dirt, other materials. Migrating additives play a big role in the adhesion process, as well as a limited number of bonding sites that are there. So before surface treatment, all of those things tend to create a hydrophobic surface. After treatment, the party gets going a little bit more, and we've got a high energy, maybe a little bit of dancing going on. We've eliminated that contamination on the surface. We've removed the migrating additives from the surface. Now those, you still may have additives that migrate, and we'll talk about those a little bit further down, but immediately after treatment, we've eliminated those from the surface. And as you've seen in the images before, we've greatly increased the number of bonding sites. All of this creates a more hydrophilic surface, or one that is more likely to wet out. So now that we understand what plasma treating is and how it works a little bit, I want to talk about how you determine the effectiveness of treatment. One of the most common ways to determine effectiveness is going to be what we call dyne testing. And dyne testing can be done in a number of ways. You can use what's known as a dyne solution, or you can use dyne pens. Both can be effective in different ways. And dyne testing is typically a pretty good predictor of success. Although I'll say, and we'll talk a little bit more in a couple of slides, it is not the ultimate predictor of success. One question that we'll often get is, what does my dyne level need to be? And we can't always give you an exact answer on that, but a general answer, a good rule of thumb, is that we want to raise the surface tension or surface energy on your material, typically about 10 dynes above that of the material you're trying to put on it. Whether you're trying to print, put a UV adhesive, a coating, whatever that might be, we're looking for about a 10 dyne level. If you don't see an increase of 10 dynes, that doesn't mean you won't be successful, but it is one of those rules of thumb that we try to shoot for. So let's give a few examples. We're going to have a number of materials on the next couple of screens that will show on where initial dyne levels go and after plasma treatment, what we're typically able to get. And so a couple of materials that are used, ABS, one that you're probably used to working with quite a bit. Typically will start out somewhere in the low to mid 30s, and we see a wide array of success with the ABS, anywhere from a 44 dyne up to a 72, which is as high as you'll go. ETFE being another good one, you're normally in the range of maybe 30, and we've got great success there, again getting to 50. That's a level that you're going to see great success in your process with. Another couple materials, polypropylene, again, another one you'll see that'll start in the low 30s and end up somewhere in the neighborhood of 45 to 60. PVC being another one. Again, you're seeing a lot of these start out low to mid 30s, ending up well into the 40s and above. PVC often getting higher than 60 as well.
And one really thing here, just to kind of help drive this home, the reason why you see a range here is that not all materials are going to be the same. So let's just take polycarbonate, for example. Not all polycarbonate materials are going to start at 37. Sometimes different types of additives, maybe the supplier, maybe if there's recycled, is it fresh material, will play into the initial dyne level. And that's kind of why we have a range too. That's why when, let's say you had a polycarbonate material, you wanted to try to treat it, I wouldn't say, hey, you'd get a 56 dyne guaranteed. That's why we have a range, and that's kind of, we'll talk a little bit more about that at the end, but just kind of wanted to point that out as you look at the ranges of surface energy levels here. It does depend on basically where we get it and what type of system we use to treat it.
Yeah, we'd love to give you an exact number, but there are a lot of pieces that come into play here. So one of the things we wanted to share, and this was a test that we had conducted with an adhesive company, and we looked at a polyethylene substrate with UV cured adhesive. And this was a test that was conducted 24 hours after the adhesive was cured. And what we saw with the control sample, that being not plasma treated, was that there was a certain bond strength associated with that. When we used our blown ion and flame treating technologies on that polyethylene substrate, we saw a factor of 3.5 times increased in strength adhesion after 24 hours. So it's a pretty significant increase in using plasma treatment with your process. So what does this mean? Ultimately, you can use a dyne test, and we can get a dyne range for your material. You can look at what's there to begin with. But the ultimate test in anything that we're looking to plasma treat is your own adhesion test, actually going through and looking at what you're doing and how your material reacts to your process. And this is really, really, we can't stress this enough. This is going to be the best test that you'll get. One of the questions that we get quite a bit as well is, how long does treatment last? And that is another difficult question to answer. It can last anywhere from hours to days to weeks to months. The effects of treatment, it varies. It varies on your material. It may vary from one material to another based on additives that are in the material as well. Humidity, contamination, time, those all factor. So what we will typically recommend is that whatever you're working with, your process, you want to incorporate plasma treating immediately prior to whatever process that you're looking to go through with your material. Sarah's now going to talk about more details relating specifically to the technologies that are available, as well as specific automotive applications and where you can use surface treatment.
All right. Sounds good. So what is atmospheric plasma? We've used that term a few times already. And by definition, plasma is a forced state of matter. Great. What does that mean? How does that relate to what I'm doing here today? Basically, what we're doing is we're charging ions. It depends on the type of technology being used, but we're bombarding the surface of the substrate to both clean, functionalize, and micro-etch the surface, as Ryan spoke about. There are 3 different kinds of atmospheric plasmas available. The first is an air plasma. An air plasma system is a high voltage arc using air. So there's no other gas involved. It's basically using compressed air, you're using a blower, and you're pushing out those ionized airs to the surface of the substrate that you're treating. You're breaking molecular bonds, and you're doing a really good job of actually cleaning the surface as well. Where air plasma comes into play, and I have a couple pictures here, I'll talk a little bit more about the technologies here in a bit, but where it comes into play is it's very good for a variety of plastics. We see this in a lot of adhesive applications as well as decorating applications. It's very versatile. It's also very nice. Customers do like to look at air plasma as an option, sometimes a first option, because your consumables are so minimal. The consumables for, oops, sorry about that. The consumables for the air plasma, Mark, you're trying to cheat here, stop it. The consumables for air plasma are just compressed air or blowers, so you're really looking at not using much in the mix. It's very inexpensive to integrate and very inexpensive to run. Sorry about that. Let's go to the next slide. There we go. Flame plasma system. So flame is another option as well. Flame is something that's very versatile, used a lot in the automotive industry. We're using a hydrocarbon gas, so we're using natural gas or propane to create the discharge. Same thing, we're still charging ions, we're ionizing ions, but here we're ionizing using a gas chemistry. This is used in the automotive industry quite frequently because of the large components that we frequently work with. As you can see, the flame plasma discharge profile is a lot wider. It can treat at a much faster rate. It's also very good at treating conductive and non-conductive materials. I should also add that any of these technologies can be integrated in a robot or in line, which I'll talk about at the end of the presentation. But you'll see different photos here as we go along. And then the third type of surface treatment or atmospheric treatment available is the variable chemistry gas plasma. This is actually using different types of gas chemistry. So not necessarily a natural gas or propane, but maybe we're using an argon, a helium, something else into the mix. We're ionizing those molecules and bombarding the surface. Some of the benefits of using a variable chemistry plasma is that it's a very low temperature process, and it also gives us a little extra boost when we're working with materials that have very low surface energy. Ryan mentioned ETFE earlier, having a surface energy of 30 if you're lucky. Most of the time it's even lower than that. When we're working with a material that has a very low surface energy, we really do need to throw everything we got at it, and that's normally where variable chemistry plasma comes into play. With that very high density discharge, it's very good also for materials that are sensitive to heat. You see a couple different profiles here, but in general you are using a gas or gases when working with variable chemistry plasma. So let's talk a little bit more in detail about the different automotive applications that Enercon works with. It's not an extensive list, but I'm going to give you a couple examples and some solutions that we've been able to come up with. So one thing that we see a lot of, and I mean a lot of, are injection molded components. It can be ABS, it can be different types of polypropylene. Some have mold release, some are very tiny, some are very large. Sometimes the customers aren't even really sure what the material is made of, but we're having a hard time bonding to them. More often than not, blown ion plasmas as well as a blown arc plasma system is used in these processes. If you have a very precise treatment pattern, you can see on the right-hand side that we're actually tracing an injection molding component prior to putting an adhesive down. Maybe you're decorating. There's an example of that here on the left of that blown arc plasma. It's just really good for being able to address just certain areas of those injection molded components, and both of those plasmas tend to be the best fit for them. I mentioned this early on, the headlamp assembly. We've all seen the moisture inside of a headlamp assembly, and that is due to that silicone adhesive coming undone from the actual lens and allowing moisture to come in. So part of what Enercon has done is partnered with a lot of automotive manufacturers out there and been able to treat these lenses, treat them with a blown ion plasma system, typically mounted on a robotic head since they all have different sizes and shapes, and basically follow along that same treatment path with an adhesive dispensing machine. It really doesn't add a lot of cycle time to it because it's already a robot already ready to go and programmed for that adhesive. So it's treating at a very fast rate, typically 100 linear feet per minute, in order to basically just apply the adhesive and move on to the next cell. I have a couple photos of what that would look like. A few of our customers have been gracious enough and shared those photos of them using an Enercon system here. Another piece is the interior panel door decorating. It can be a lot of different kinds of plasmas that we work with, but I mentioned earlier that flame plasma is a really good fit for panel decorating. And the nice thing about panel decorating is they have a lot of very large components. Sometimes they have a lot of complex shapes. Working with a flame plasma system, you are actually able to treat in and out of all of those complex shapes, and typically on a robot as shown here, and being able to do it in a very quick cycle time. Typically we're working with customers demanding a 20-second cycle time or less, and we're able to achieve that. And along that same line, I just kind of want to talk a little bit about flame burners. A lot of you may be familiar with flame treaters. You may have them already installed at your facility or have worked with them in the past. It may be something that we'll call more of a homemade system or more of an inexpensive system. This is kind of where I like to point out a couple pros and cons to working with a homemade versus a system that is specifically designed for surface treatment. The top photo here is a traditional ribbon burner. This is most commonly seen, especially if you are working with something that has been put together at your facility. It's a cast iron body. It has basically the ports that come out of it look like a ribbon, which gives it its name. Sometimes it has to be water cooled, but basically you've got air and a gas mixture, the natural gas or propane, pushed out of the head, and it's able to treat the part. The downsides of working with a ribbon burner are a few things. One is that it's a cast body, meaning that you can't take this burner apart. So if some of the ports start to get clogged or dirty, the only way to address that is to literally replace the entire head, which is a big downside. It can cost, a lot of money as far as replacing components goes. The other piece, and probably a really good piece to mention here, is if you're thinking about putting a flame system on a robot or working with a very high-speed application, you're not going to get the velocity out of the head like you would with a different type of design. We actually make a port-style burner, and you can see that on the bottom right hand of your screen. It's an aluminum body, and they're actually drilled. And if you were to look at this from a side-angle view, you actually see that they're conical in shape. So when you push that air and that gas through the head, you get a higher velocity discharge. The benefit of that is you can have increased line speeds. You have the ability to take the head apart and clean it, which is very nice, so you don't buy new components all the time. And that you're going to get treatment from edge to edge. If you have a 100-millimeter burner, you are going to get 100 millimeters of treatment from edge to edge. It's not going to come to a point where you're getting treatment a little bit better in the middle versus on the sides. Just kind of wanted to point that out to you. Some of you have probably seen these ribbon burners, but this is a really neat component that Enercon manufactures with their flame plasma treaters. And then to continue along the line of flame treaters, another application out there is wrapping and foaming applications, specifically for dashboard assemblies. So while some customers are decorating or painting, you can also apply the same type of technology if you're leather wrapping or foaming the dashboard assemblies, typically done with a flame system on a robot due to the complex shapes that we work with. Going along a different line, I'd like to talk a little bit about marking in wired cable as well as potting. Depending on where you are in the supply chain, you may be working with the smaller components to automotive vehicles, and that might be actually applying ink to the surface of a wire or cable. Same concept we have here on the left-hand side of the screen, a blown ion plasma system, pre-treating a wire prior to perhaps putting a digital inkjet a code on. You could also be using a contact wheel to do that. Important that that ink stays adheres through installation. You don't want that ink rubbing off and then the assembly team looking at it and going, well, where does this go? Yeah, it might be a different color, but we're not really sure what exactly this wire cable is intended for. So that is that industry is becoming higher and higher demand that ink stays adhered. It is a less expensive alternative to laser marking. Laser marking can be very expensive. If any of you have gotten into that, so we do recommend considering plasma if you have that challenge. Another would be potting. In the bottom right hand of your screen, you actually see that blown ion plasma in a gun form. This is a handheld version that Enercon manufactures. You may be working with a potting between wires and a plastic component. This will allow you to, by hand, treat, maybe for smaller volume assembly, and pop that wire in there for better adhesion. In today's cars, there's a lot of electronics that go into it, so you may be on that side of the supply chain. When we're working with different electronics, obviously we don't want the plasma to affect the surface of the component, but we may still need to bond to it or coat it. Actually, the flame plasma does a really good job of this. It's able to treat, clean, micro-etch the surface, and prior to coating without actually affecting the surface of the circuit board. This is kind of a neat application, and it's come up more and more. If any of you worked with metal components, so this is really specifically for metal, where you need to degrease them. You have leftover machining oils on the surface. Just simply you need a better clean site prior to bonding, or maybe you're not even bonding. Maybe you just literally need to clean the metal component prior to installation. Both the blown ion plasma and the flame plasma are both really good alternatives to inexpensive, costly, time-consuming thermal degreasing oven. We've actually seen this more and more. Our customers have been able to literally replace equipment that can take up an entire room with a very small footprint flame treater. And by no means are we limited by a certain type of profile either, because of the versatility in the different systems. And some of you might be in the R&D section and looking for something for a little bit of proof of concept. Also consider that there is a handheld blown ion plasma system. It's designed for handheld use. It's designed with safety in mind as well. So if that's something that you're looking for, just being able to do small volume of proof of concept, that is another application that we've sold into the automotive and really a lot of industries for that use. And I mentioned this early on, door gasket applications. This is another alternative. You can see the blown ion plasma on the bottom right hand of your screen, but you actually see it with multiple heads. One customer demand that we frequently get is not only can we treat, but can we have a little bit more monitoring capabilities. And by the way, I also need to have multiple heads in order to cover this entire door panel and meet our cycle time. So by using what we call our Dynamite IT Elite, it's a multiple head blown ion plasma system, customers are able to meet all those demands and actually get quite a bit of data feedback from the blown ion plasma system as well. And to take all of that information I just shared, I would like to ask you to think back to that original question that I asked at the beginning. What challenge are you facing now? What could you be facing in the future? What have you faced in the past? And think about how we would approach it. There's a few ways we start with every application. We mentioned that not all material treats the same and not all applications are the same as well. A couple questions we ask. What material are we working with? Is it conductive or non-conductive? Some types of treaters are better suited than others for conductive materials. Where are we treating? Are we treating a small glue path? Are we treating the entire dashboard? What kind of expectations are you looking to get out of the treater? How is the part handled? Is it a manual operation? Is it on a conveyor? Is it on a robot? How fast do we need to treat? Do we have all day? Do we have 20 seconds? What kind of volume are we working with? Is this going to be a multi-cell application? Are we going to be doing 100 parts a week? And we take all of that information and we ask you then to send samples to our lab. We actually have a lab that allows you to try any and all of these technologies, as well as quite a few surface treating experts available to you to kind of help guide you what might be the right type of technology. Once we get the technology, kind of figure, well, we got one or two options maybe we're working with, we then talk about integration. So and there's a lot of different ways you can integrate. You've seen photos here today of them being used both on a conveyor or offline. You can mount it over your existing equipment, so you don't necessarily have to create a whole new cell for this. It can be configured with an indexing system. It can be a rotating wheel. It could be right there actually on a robot within a cell as well. There's a lot of different configurations. And the key point that I'd like to make is all of these technologies can be integrated with your own control system. So it's not as daunting as it may seem to be able to integrate it. You might be already thinking, well, okay, great, you have a solution. How's this going to work? There's a lot of different options available to you. We work with you and your expectations. We also help you with operation tips. Every treatment system will have a specific type of distance, dwell time, and ultimately put it to the test adhesion. So there's a lot of options available to you when it comes to treaters and how to integrate them, and that's where our experts come into play, and that's what we're here to help you with. I'm going to do a quick review here, and then we will open up the floor for questions. If you have any, please feel free to start typing them into the question window. We'll get to as many as we can in the time frame that we have, and if we don't get to a specific question, Ryan or myself will be following up with you individually. Surface treatment, it cleans, functions, and micro etches the surface of a material to improve adhesion. You can improve your bond strength, your line throughput, you improve your process, you're reducing waste, reducing costs. Flame and plasma are both used in a wide variety of applications, which we just went through: paint, coating, ink adhesion, adhesives. They're sometimes just for cleaning, such as thermal degreasing. You can integrate them in really any way you'd like. There's no limitation when it comes to that. And at the end of the day, we have a lab available for you to test these out. That's typically the best first step that customers take when they are working with a material they're having challenges with. I am going to open the floor up now to questions. Like I said, please feel free to type any in as we go along here.
So the first question that we have, Sarah, is, can you comment, is there a most popular treatment system that's used in the automotive industry?
Well, that's actually a good question. Because there's so many different treatment systems available, I wouldn't say that there's a popular one. I would say probably more commonly the flame plasma is used because of all the different types of shapes and sizes and configurations. That particular system lends itself well to that, but I would not say that you'd be limited only to that just because you have a large component. So let's say, for example, you have a dashboard. And yeah, you have a dashboard, but you only need to draw in a line for beaded adhesive along the outside edge. Just because it's large doesn't mean you need to go to flame. You could use a blown ion plasma or blown arc plasma actually in the mix as well.
All right. Can you tell the audience a bit more about how we actually increase the number of bonding sites?
So that's a good question. So Ryan showed us a photo early on of a microscopic photo where you actually see a treated versus untreated. When you are treating a material, you are micro-etching it. So think about you applying a sandpaper to the surface of something and roughening it up, but on an extremely microscopic level. So to the naked eye, you don't see any different. You're not changing the structural integrity of the component. You're not visually seeing that roughness that you would with a sandpaper. But on a very microscopic level, you've physically created more peaks and valleys. So when you apply that adhesive down, it has more to grab onto. And that's what we're ultimately trying to do here with plasma and flame.
Great. What about when we talk about cleaning, what do we mean by cleaning? Do we clean off fingerprints, release agents? You know, I think you talked a little bit about maybe machining fluid, machining oil.
Mm-hmm. That's also a good question. So cleaning is an integral part in the surface treating process. So I'll kind of take a step back and answer it this way. If you have a plastic component, a lot of times, if you're having a hard time getting a good bondability of adhesive or an ink, you might take like IPA or a solvent wipe and clean the surface. You wipe it off. Part of that is you're physically getting rid of dust, fingerprints, oils, whatever else might be organically on the surface. Does it work? Yeah, it works. It's you know, at the end of the day, you're getting rid of that. So, but the nice thing about plasma is not only are you replicating that and able to get rid of that wiping process, you're also cleaning other things off the surface. So one of them is a release agent or a mold release. Mold release is commonly used, obviously, in plastics manufacturing. The problem is when you go to, let's say, put an ink down on a plastic that has mold release, you're not really putting the ink on the plastic. You're actually putting it on the mold release. Well, it can probably guess what would happen. I mean, mold release is designed to not let things stick to it. That's its general properties. That's what it's designed for. So that's why a lot of times, let's say, the ink is adhering really well. Now, when you clean with plasma, you are also removing that, where maybe a solvent wipe wouldn't be able to do it. It could, but probably not. And you are also allowing for anything that's migrating to the surface to be cleaned off. Now, really early on in the presentation, Ryan mentioned how sometimes materials will still migrate to the surface, which is why you want to treat and then print as soon as possible. So when you are cleaning, you're cleaning to the depth of a point where you're sometimes creating a path of something else to migrate to the surface. When it migrates to the surface, you're kind of back to where you started, unfortunately. So let's say that is a problem. We do have fingerprints, oils, and possibly something that's migrating, and we treat and we print right away. That's the best scenario because now you haven't allowed anything to migrate to the surface. You've also gotten rid of anything that's organic on the top of the surface out of play, and now you've got that ink to adhere. The time now is no longer relative because now you have as permanent of a bond as you're going to have.
So, Sarah, what you're saying is that once you lay down an ink, an adhesive, a coating of some sort, that is then permanent. That time release has nothing to do with it once you lay that down.
That's exactly it. And I also would like to add too, just by plasma treating isn't going to allow you to get away from like a secondary process. So let's just say your adhesive is a UV curable adhesive. It's not going to allow you to no longer use a UV curable light to cure the adhesive. You still need to do that. Or let's say it's a water-based adhesive and it requires a 24-hour cure time. You still need to follow the cure time that's instructed by the manufacturer of that adhesive. It's not going to decrease that time. So it is important that, yes, it is as permanent as it's going to be, but you still have to follow the instructions related to the ink, the coating, the adhesive that you're working with. You're going to find, though, once you've done that secondary process or waited for that secondary amount of time, that your actual bondability, your pull strength between those two components has strengthened.
And I think we talked about that a little bit in one of my slides earlier, in just the fact that we measured that bond strength over a 24-hour time period, not immediately after that was UV cured. So that's an important piece.
The common misconception that it'll let you skip that step. Unfortunately, you still need to follow the steps related to that.
Yeah, one of the things that just popped into my mind, Sarah, that another question that was spawned from the fingerprint piece is talking about handling of the parts and handling the parts after they've been treated, but maybe before adhesive has been put on, or painting or coating, whatever it might be. Can you talk to that? Can you talk about handling the parts after treatment but before whatever process you're trying to
follow? Yeah, sure.
Yeah.
Okay, so if you were to say you're working with an ABS part and you're running it through a plasma process, and maybe your process is a little bit more hands-on. It's not all done robotically, and now you've got an operator that is picking up that freshly treated ABS component, moving it onto the next station where it's going to be painted. That operator is not wearing gloves, has finger oils, or maybe is wearing gloves, but they're pretty dirty, and is picking up the part and moving it over to the next station. What happens is now we've basically we'll call recontaminated the part, so to speak. Those finger oils are now going to be present, and once again, you might be dealing with the problem you had before you plasma treated. So in a nutshell, it's really important to look at your whole process as you integrate plasma. Make sure that you are not over-handling the part, as well as not allowing too much time between treatment and bonding. Same scenario, take a freshly treated part, ABS part, and you stick it on the shelf and you come back to it 2 weeks later and try to print or put a coating on it, you may have the same problem, that surface energy is worn off. Just good to kind of look at the bigger picture.
All right, we've got a question about length of treatment, and could it be possible to make surface treatment longer lasting with multiple treatments of the same surface or something of that sort? Is there a way that you can make the treatment last longer?
There are a couple types of technologies that tend to hold their surface energy a little longer than others. I know we mentioned that surface treatment is not permanent. Nothing is permanent. But we do know that when we are working with a material, sometimes it's not always feasible to print or bond right after treatment, that we have to look at this as an alternative. The flame plasma system and the variable chemistry plasma systems tend to hold their longevity the longest. What really is the driving factor isn't necessarily the technology, but it's really the material. There are materials out there that we know historically do not hold their surface energy very long, and when we start to work with those materials, we'll actually kind of preface the customer with saying, hey, you've got a very short window. Necessarily going over them multiple times with different technologies may give you a little bit more time, but it's really, it's more material driven than it is technology. You may be kind of wondering what those materials are. Typically anything that has a lot of plasticizer in it is very bendable. Silicone is kind of a culprit. Rubber is a culprit. Where we know historically we can treat these materials, we just have a very short window.
Sure.
Yeah, and then we know that other plastics can tend to hold them longer, and we'll kind of work with you on what the material is and what we've seen historically as far as longevity goes. But I mean, at the end of the day, we always recommend you do your own testing if you're not planning on bonding soon after treatment. It's the only way to really know.
All right. What about, let's say I treat a part and the next machine down the line breaks down, and it takes me a week to get that fixed. Now the surface energy has gone down on my part. Can I retreat those parts?
You can. And I say it hesitantly. You can retreat a part to bring the surface energy back up. We could basically bump treat it back to where it's at. There's also a phenomenon, and this does happen actually more often than you'd think, where we can actually over-treat a part. So let's just say, for example, your machine breaks down, and now you need to, oh, I don't remember if I treated this part, or it's been sitting online for a week, or maybe it's only been sitting online for an hour during break time. And either you don't remember if it's been treated, or you did, but you're just not sure what kind of surface energy it has. To go over and retreat the part, if the surface, it could potentially harm it. More isn't always better. So one swipe over a part and you get good surface energy, 2 may still be fine, 3, 4, 5, 6, it depends on the material, depends on the technology, but we can actually start to see the material, the dyne level degrade. And sometimes we don't even see the dyne level degrading. We actually see that it's still at a very high surface energy, but we've actually started to damage the part on a molecular level. So, it's not a really good answer to your question, but it could be fine or it could not be. My recommendation is either to do extensive testing related to this, or just have a protocol in place where that part gets recycled, and you move on.
How far does that treatment reach into the material?
Well, I'm guessing there's 2 different ways this customer is asking this question. So one might be depth-wise into the material itself. Really only treating angstroms deep, so it is very shallow treatment. It's not, which is nice because you're not actually affecting the properties of the material. If you're asking the question relating to how deep can you treat into a complex shape, it relates more to the type of technology you're using. If you have a very complex shape, I would recommend the flame plasma system because your throw is much farther on that. Typically, you can get between 1 to 5 inches of treatment away from the head, where those air plasma systems, you really can only get about a half of an inch away from the head discharge. But regardless of the technology, we're only treating in angstroms as far as depth into the material.
What about cost? What's the cost of a system? I mean, it's always a question people want to know, and I know it's not always an easy question to answer, but can you give us an idea where things tend to sit?
Well, when you're looking just at a plasma system, so we're not looking at the robot, we're not looking at the conveyor, we're not looking at installation, just simply looking at the power supply and the head related to it. It really depends on the technology, but to give you guys some ballpark figures of what you'd be looking at investing in, you're going to be running anywhere between about $7,000 to about $17,000, depending on the type of equipment. If you've got a lot of, you say custom equipment, obviously would fall outside of that, or maybe you want a lot more integration or help that way, you're going to start getting up a little bit more in cost. But if you actually look at the cost of this atmospheric treating equipment versus, let's say, a chamber plasma, which we didn't talk about today, but it is an alternative to atmospheric treating. It's where you actually have a chamber, a physical box of some sort, where you put the part in, shut the door, and it treats it. You're looking at a fraction of the cost, which is really nice. And the other thing to consider from a cost perspective is not just the investment in the equipment, but also the consumables being used. So let's just say you can integrate an air plasma. I'm just using a number for $10,000 for the equipment. You're only using compressed air. It's not costing you a lot to pay for that compressed air, where maybe a chamber plasma or an alternative, maybe buying expensive solvents and that kind of thing, really is going to pay for itself pretty quickly. So depending on where your budget is too, I mean, if you have a limited budget as to what you're working for, always good information for us to know on the front end. We can kind of help you, size you with a system that's going to work with that as well.
Yeah, when you're running samples, how do you choose which system is best for someone's product?
Oh, this actually kind of brings up a good point too. So with specifically Enercon, I mentioned we have a lab that has every type of technology available for you to trial. The benefit of using Enercon's lab is that Enercon manufactures every type of atmospheric surface treating technology available today. So when you bring in a project to us, we won't specifically recommend the one thing or the two things that we manufacture. We may have more than one solution to you. We listen to you and we ask those questions that I mentioned earlier. What's the material? What's your throughput? What are you looking to achieve on the front end? And sometimes we only come up with one solution, but many times we come up with more than one. And then you get to actually decide what's going to be best for your application. Sometimes it's going with the least expensive. Sometimes it's what's the easiest to integrate. But just to kind of give you my shameless plug there, that's really kind of a benefit to you, is that you can try more than one system here at Enercon, more one technology, I should say.
Sure. It looks like we got about time for one more question, Sarah. We've got a question kind of talking about, we've talked a lot about plastics and metals and different glass and different things. Do we have any experience treating things like cotton or paper or other materials?
Mm-hmm. So we actually do. We've been specifically speaking about three-dimensional object treating today, which we call atmospheric surface treating. Other alternatives that Enercon actually manufactures in a different area of what we do is treating roll-to-roll materials. So cotton, paper, a lot of the times those are in a roll form or in a sheet form. We do have quite extensive experience doing that. We use a slightly different type of treater. We do use a corona treater or a plasma treater. So if you are interested in exploring those options, whether it be in sheet or roll form, we do have a whole team available to kind of answer your questions relating to those materials. A lot of times trying to get a coating or an ink to adhere to them is the ultimate goal.
Great. Thanks, Sarah. I want to thank all of you for joining us today. As Mark mentioned in the beginning, we are recording this session. We'll have the recording of the webinar available here in the next couple of days, maybe an early Christmas gift for all of you. Any questions that we did not get to,